Welcome. Today I'm going to talk to you guys about adding extra tools to your mathematical toolkit here. So far we have three formulas. I don't know why I did that. Three formulas. The first formula is the average speed equals the displacement over the time. The second formula is that the average speed also equals the initial speed plus the final speed divided by 2, because it's an average. And the third formula is the average acceleration equals the change in velocity divided by the change in time, or the change in speed divided by the change in time. Those three formulas, I did it again, there you go. Those three formulas there can be put together algebraically to make two more useful formulas. And I'm going to give you what those two shortcut formulas are in this video right here. And I'll give you an example of how to use each so it makes sense to you. And you can hopefully see the difference between the two. I hope so. We'll see. Okay, again, this is the 14th video. It's on motion calculations, and let's go. First question I have is, how do I solve acceleration problems in which I'm given the time? I do not mean that I'm giving you the time to actually do the work. I mean, in the problem, you see that there is a time measurement that's given. So I'm going to start off by giving you a scenario, and the scenario looks like this. I have a ramp. Physicists love to do ramp problems. And on this ramp is a ball. And the ball, the first time it's observed, happens to be right there. So the first time it's observed, you might remember, we're going to go ahead and signify with a t sub 1, and we're going to call that time equals 0 seconds. That's the moment that we start to observe it. Now, at that moment, it has an initial speed. We didn't see it right away, so we only came in later on. So sometime in the past, it must have had 0 speed and then accelerated, but we didn't observe that stuff. So its initial speed, or velocity, because I'm going to give you the direction, is 2.0 meters per second. Now there's no direction there right now, so I have to tell you something about one-dimensional problems. So you guys are familiar with the fact that we have a horizontal axis, that we talk about motion going horizontally across, either in the positive direction or the negative direction. If we have a ramp, all we do is we tilt up that axis. So now instead of being perfectly horizontal, it's now tilted, because really the ball can either go up the ramp or down the ramp. It can't go any other way. So instead of having left or right, now we have up or down the ramp. So I'm going to go ahead and define, and I'll change my color here so it makes more sense. I'm going to go ahead and define down the ramp as positive, and I'm going to define up the ramp as negative. Could I have switched those? Absolutely. If I wanted to, I totally could. There's actually a good reason to switch them, and that is that usually when things fall, they fall into the negative direction. And this is kind of falling down the ramp. But if I leave this positive, I've actually made my math a little bit easier. So I'm always trying to find the shortcuts, the laziness that I can work into any problem. And so I've just sort of defined it as positive. So I'm going to go back down to my speed here, and I'm going to make it a velocity by adding in the fact that it's positive down the slope. So it has this, this velocity right here. Now, I don't actually have to put down the positive because I'm also putting in the vector to show you which way it's going. But because adding the positive makes the algebra easier later on, that's why I've done it. Okay, so my question for you is, what happens if it's rolling down this ramp? Well, in a perfect world, if I'm not worried about friction or other things, it's going to accelerate down the ramp. Of course, it's going to accelerate down the ramp. That's why we go sledding or go skiing. It's because we like to accelerate down the hill, get faster and faster and faster. That's what makes it exciting. So this ball is going to accelerate down the ramp. Let's imagine that its acceleration down the ramp, which of course is an average acceleration, is 2.0 meters per second squared. So what does that mean? That means that it's accelerating 2.0 meters per second every second that it goes down the ramp. So it starts off, initially we'll see it going 2 meters per second, and then it should go, after 1 second, should be going 4 meters per second, and after 2 seconds, it should be going 6 meters per second. That's what that means. But that only means that if their acceleration and the speed are in the same direction. And since they're both down the slope, they both are in the same direction. And so this was positive, as I said just a minute ago. I'm going to go ahead and make this positive as well. Now my question for you is this. If I wanted to, I could ask you, how far does the ball get down the ramp? So I want to know how far it gets down the ramp at time equals 4 seconds. So here's where it was 0 seconds. It's going to be down the ramp here as it rolls down for 4 seconds. It's going to be someplace down the ramp. And so since I'm talking about its position here compared to its position there, I'm really talking about something that looks like this. A vector that starts here at its initial position and then moves down the ramp to its final position. Do you remember what that kind of vector looks like? What we really call that? Yeah, that's a displacement vector, right? So when I say how far, I'm really asking you about its displacement. So it starts off here at 0 seconds, and it ends someplace at 4 seconds, but I don't know where. Now, I could use those 3 formulas we talked about earlier to take lots of steps to be able to solve this problem if I wanted to. But as you know, I'm pretty lazy, so I'm going to give you the shortcut. I will make another video in which I derive this if you're interested, but I'm not going to make you watch it. If you're interested and you're a mathematical person, you love algebra, you're a weirdo like that, like I am, that's cool. Watch that video. I'm not going to do it here for you. So this equation is actually 2.4 on the formula sheet, and it looks like this. The displacement of an object is equal to its initial speed or initial velocity multiplied by the amount of time over which you observe it plus 1/2 times the acceleration that it experiences multiplied by the change in time squared. Now it's important to remember that that exponent only goes with the change in time. It doesn't go with the acceleration or the 1/2. So it's delta t squared. That's it. Okay. So this I like to call the master equation because it really can solve probably 90%, maybe 85% of your one-dimensional math problems in physics. So if I ever say use the master equation, I'm talking about 2.4 here because, again, it's the most useful, I think, the most useful of all the equations in the first linear motion unit. Okay, so let's try to solve this here. Where does it end up located? So where is this delta x? So that's what I'm looking for. So it's already solved for the right thing, which is fantastic. So now I'm just going to plug and chug. So delta x, I'll give myself a little bit more room here, and I'll start in a different color. So delta x is how far? That's what I'm looking for, is equal to the initial speed, so that's 2.0 meters per second, again positive, multiplied by the amount of time that you're observing it. So I'm going from 0 seconds here at t1 to 4 seconds at t2. So it's a time of 4.0 seconds. Added to 1/2 times the acceleration, and I said the acceleration down the ramp was positive 2.0 meters per second squared, so I'm going to go ahead and put that in there. Positive 2.0 meters per second squared times the time squared, and the time squared is 4.0 squared, 4.0 seconds. Ooh, almost out of room there. There we go. Perfect. Now I want you to notice something interesting here. Let's just look at the units here because I wrote them in for a special purpose. Meters over seconds times seconds gives us just meters. Isn't that exactly the kind of unit that we're looking for when we ask how far something is? So its displacement is measured in meters. That's a good sign. Let's go back over here as well. We have no units for 1/2, obviously it's just a constant, and then we have meters per second squared, and then we have seconds squared. And so what happens to the seconds squared on the bottom here and the seconds squared on the top here is that they cancel. And what's left? Just meters. So we have meters plus meters. Isn't it beautiful when it all works out that way? Let's do the math. So delta x is equal to 2 times 4. Now there's 2 sig figs and 2 sig figs, so I'm going to go ahead and leave my answer as 2 sig figs. So that's 8.0 meters plus, what's 1/2 times 2? That's just 1. And then 1 times 4 squared, so that's 16. So I end up with 16 meters. And I'm going to ask you a question here. How many sig figs does this have? 2. How many sig figs does this have? 2. And so my answer can only have 2 sig figs. 1, 2. That's it. So it's 16 meters. No decimal. Okay, so I'm going to do my last step here. I'm going to combine those two together. I'll use blue. Interestingly, notice what happens. I'll stack them so you can see here. 16 plus 8.0. Using our sig fig rules, we can only use the ones place because for the 16 we don't know what's in that tenths place. So I have to chop it off there. So I end up with 24 meters. That's it. That's all I get for sig figs. And so my delta x is equal to 24 meters. So that's how I get my answer. Now I've used this 2.4 to be able to solve it. Pretty easy. It was a lot of plug and chug. Where it gets more difficult, a little bit, not terrible, just a little bit of more algebra gymnastics there, is when you're asked to find what the acceleration is. So now you have to rearrange this problem to be able to solve for a by itself. And that gets a little bit trickier. But you can make your life about 1,000,000 times easier by choosing to make that value right there 0. If we had observed the ball from the moment it started rolling so that its initial velocity was 0, what happens to this whole term is that it goes away. And then we just have delta x equals 1/2 at squared. And that makes your life so much easier if you can get rid of that. It's so much easier to solve for a if that's the case. And so my suggestion, as always, is to be lazy and to be smart. And that's to choose your initial speed as 0 as often as you can. Okay, so that's your first one. Now your second looks like this. How do I solve acceleration problems in which I'm not given the time? So let's take a look at what that looks like. Again, we have a similar situation, only in this case we are not given the time. We're given the displacement instead. So we have another ramp, like so. And at the moment we observe the object, let's say it's another ball rolling down here. At the moment we observe it, its initial position, we're going to say, is 0. Because I can define wherever I want my 0 mark. So I'm going to say it's 0 right there. Its final position at the end of my time observing it is, let's say, 8.0 meters away from that initial position. So this is my reference point, and this is my final position right there. So if I wanted to, I could go ahead and figure out what the displacement would be, right? So the displacement would be down the ramp. So it looks like this, like so. Delta x equals, and we said positive is down the ramp, right? So positive 8.0 meters. It bugs me that it doesn't have a good time with the decimal there. Okay, let's say that the ramp is the same as before, though, and that is that the ball has an initial velocity. So it's the same situation as before. the initial velocity for the ball is positive 2.0 meters per second. And the acceleration that the ball experiences down the ramp is again 2.0 meters per second squared. Okay, so the question that I would have is how fast is the ball going right there? So how fast is asking about velocity. And so the question that I want to know is right here, what's v sub 2? How fast is it going by the time I have stopped observing it right there? You don't see any time in there, right? So we can't use 2.4 to be able to solve this. So we have to have a different solution. And that solution here is 2.5, which looks like this. Now this is one that I think a lot of people get confused about, so be careful. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. There we go. So that's our fifth formula for physics right there. And I call it the no time formula because, not that you don't have any time to use it, but do you notice that there's no time in the equation itself? So this would be something that would be specific to situations in which you wouldn't have the time. Now, for us doing experiments in physics, we find it very easy to measure time, and so our experiments oftentimes will have time, almost always. So this doesn't get used quite as often as a result, which is why I said the other formula would be used about 85 to 90% of the time. This one is the one that you'll use for the remainder of the time. But I'm going to go ahead and solve, and so we'll see how this works here. V sub 2 squared is equal to, and I'm going to have to take away that squared at some point, so just keep that in mind, is equal to our initial speed, our initial velocity squared, so positive 2.0 meters per second squared, plus 2 times positive 2.0 meters per second squared times 8 meters. That's a positive 8 meters there. There you go. That's pretty messy, but you get the idea there. So I want you to think about this for a second here. How do I get rid of that squared right there? Well, I have to actually square root everything under it. So I'm going to go ahead and rewrite it here as everything under the square root sign. But I'm going to try to solve some of it as I go here. So this is positive 2 squared. So that's positive 4.0 meters squared per second squared, plus 2 times 2. Now this 2 is a perfectly known 2, so it doesn't count in the sig figs, so don't worry about that. So 2 times 2 is 4. 4 times 8 is 32. So we only have 2 sig figs in this and 2 sig figs in that, so we only get 2 sig figs in our answer. So 32. Now it's meters over second squared times meters. So the answer is meters squared per second squared. Now you may notice that this is meters squared per second squared, and this is meters squared per second squared, and then we have a square root over it. So we're going to get rid of that. So in the end, we'll only have meters per second, which is perfect. Nice job. Okay, so I'm going to add these two together, and I'm going to switch up here. So 32, there we go, plus 4.0 equals 36. And unfortunately, that decimal goes away there. So 36 is my answer. So V2 is equal to the square root of 36 meters squared per second squared. Or In this case, the answer is just 6.0, because we have 2 sig figs, meters per second. So there you go. At the end of 8 meters, how fast is it going? It's going 6.0 meters per second. Easy enough. So again, it turned out that this was already solved for the most part for us in the right format. It gets a little bit more complicated if we are looking for the acceleration, just like before. So to make your life a lot easier, what can you do? The exact same thing you did before. How do you make this formula easier? You choose a position in which your initial speed or initial velocity is 0, and that will make your life so much easier. So my suggestion to you is always to be smart about how you're setting up this problem. Choose that as often as you can to be 0, and then you just have a very simple formula to solve. Hopefully that works. Okay, with that, I'm going to go ahead and wrap things up. I want to thank you guys for watching. Please make sure you're working on those note sheets and those interesting question forms. I'd love to have a great discussion. We're going to do a lot of practice problems on this. So if you're feeling like you're a little concerned or a little uneasy about doing it on your own, that's totally okay. We're going to use these all throughout the entire year, so you want to make sure that you know how to do it, of course, but we're going to do lots of practice to make sure you're ready for it. Thanks for watching. Have a great day.